All right, let's jump right in. We're going to explore a really fascinating problem in MRI. How does a scanner actually figure out where millions of different signals are coming from inside your body?
So, to start, we really need to get a sense of just how big this challenge actually is.
Think about this. A single standard scan can pull in signals from over 4 million tiny points. We call these little guys voxels. You can almost think of them as 3D pixels. And every single one is sending out its own signal. But here's the problem. The scanner's antenna, it picks up all 4 million of those signals at the exact same time. And they all get mixed together into one big, jumbled up mess of a signal. It's totally indecipherable. It's kind of like trying to record everyone in a massive stadium talking at once. All you'd hear is this big, buzzing sound. You completely lose all the spatial information. You have no idea who said what, or more importantly, where they were sitting.
So, faced with this total chaos, how on earth did scientists figure out a way to solve this?
Well, they came up with this incredibly clever solution using something called a gradient field. It's essentially a small, precisely controlled magnetic slope that gets layered right on top of the main, powerful magnetic field. And what this slope does is make the total magnetic field strength change in a perfectly linear, predictable way across the body. Okay, before we get into the nitty-gritty physics, I've got a simple analogy that's going to make this whole concept click. So imagine you've got this huge choir. If the magnetic field is uniform, it's like the conductor telling every single person to sing the exact same note. Let's say middle C. All you hear is this one single monotonous hum. You have no clue if a sound came from the front row or the back row. But now, in steps our smart conductor. This is our gradient field. He does something different. He tells the front row to sing a low note, the middle rows to sing a medium note, and the back row to sing a really high note. And just like that, the puzzle is solved, right? Now, if you hear a high pitch, you know instantly it came from the back row. A low pitch, that has to be from the front. So here's the big aha moment. By assigning different pitches, or, in more technical terms, different frequencies to different locations, we've created a direct, unbreakable link between the sound and its specific origin point. Okay, so let's take that exact idea, that conductor's trick, and see how it helps us transform that messy MRI signal into a super precise map of the human body. At first, just like with our choir, the scanner's antenna gets this one single chaotic signal. All the information from those millions of voxels is just jumbled up inside. You can't tell what's what. Now for the key step. At the precise moment we're listening for the signal, we switch on the gradient field. This is the conductor's cue. And what happens next? Well, it's kind of like a miracle. That one messy signal splits apart, almost like white light through a prism, into many clean, separate signals. And here's the key. Each one now has its own distinct frequency. So now the machine can simply analyze the frequency of each signal component to reverse engineer exactly where it originated. A high frequency means it came from the high field side of the gradient, and a low frequency from the low field side. The location is now encoded right into the frequency. Of course, our bodies are three-dimensional, so mapping location in just one direction isn't enough. We need to be able to pinpoint every single voxel in 3D space. And the solution, conceptually, is actually pretty simple. We just use 3 separate gradient fields. We've got an X gradient to vary the field from left to right, a Y gradient for top to bottom, and a Z gradient for front to back. That Z gradient is also crucial for selecting the specific 2D slice we want to image in the first place. So by skillfully combining and rapidly switching these 3 gradients on and off, we can effectively give every single voxel in the body its own unique frequency address label. And what's really cool is how elegantly this entire physical process is captured by a little bit of mathematics. This formula right here is the very core of spatial encoding. Now, I know it might look a bit intimidating, but its meaning is actually very straightforward and incredibly powerful. All it's telling us is that the total magnetic field, B, at any point, is just the powerful main field, B0, plus the small additional field from the gradients at that specific location. And this brilliantly illustrates the key. This simple addition creates a permanent linear link between a physical location, its X, Y, and Z coordinates, and the signal frequency it will produce. We've turned a hard geometry problem into a much easier signal analysis problem.
This whole process has a name. It's called spatial encoding. It's simply the ingenious use of gradient fields to build a robust bridge between a voxel's physical location and its signal's frequency. Once that bridge is built, the scanner's computer acts like a master audio engineer, separating out all the frequencies to assemble a detailed image.
But this immediately leads to the next puzzle. We now understand how to use frequency to determine position along one single direction, yet MRI images are two-dimensional slices. So how is it possible to pinpoint every voxel on an entire plane when we only seem to be encoding one axis with frequency? There must be another trick involved, and that is what we'll explore next time.